Okay, question 47. Draw resonance contributors and indicate major and minor contributors. This is very similar to our first question, question 40, I believe. Yeah, question 40. All we're doing here, the only difference is we're trying to say, of the potential resonance forms, which one's the most stable, okay? So I'm going to go relatively quickly about how I move electrons around, just assuming that everybody's on board with that idea. And then after that, we'll talk about how you figure out major and minor. Okay, so question 2. Let's go through the most obvious resonance contributors for this guy. So let's go ahead and discount the resonance contributors where we move electrons around the ring like this. Okay, so this is one possibility, and we get a resonance contributor that would look something like this. And that's totally okay. There's nothing wrong with this resonance contributor, but there is no major difference in terms of form between this white and the green, so might as well not even worry about it. There is no energy difference in between the two. Okay, so we'll go ahead and forget about that and go ahead and get rid of it. And so let's move on to drawing resonance contributors that actually have formal negatives and formal positive charges on them. Those are just easier to play around with to talk about energy differences. So let's go ahead and do the most obvious one, where we can take this pi electron on the phenyl ring and move it up to this carbon-carbon bond. So if we do this, it should be obvious, hopefully at this point, that we cannot stop here. We actually have to do another resonance form. This resonance form would include this pi bond being broken, moving up to the oxygen. So going back to our mantra, we make a bond, we have to break a bond. So we've made this bond between this carbon-carbon, so we're breaking this bond between the carbon-oxygen. Okay, so this is one possibility, and if we do that, this is what we would get. Again, six-membered ring. We're going to have a pi bond on this carbon-carbon bridge. We're going to make the carbon-oxygen single, and then from here I'll just draw in all of the lone pairs. And at this point it should be obvious that oxygen is negative, then this carbon right here is going to be positive. Okay, that is one possibility, one way you could do this. Let's go through a less stable resonance contributor possibility. Okay, sometimes what I'll see is students like to draw this kind of thing where you have the carbon-oxygen double bond being broken, but instead of pushing electrons up to the oxygen, sometimes they'll push them onto the carbon bond. So again, kind of doing the same thing where we're making this carbon-carbon double bond, but we're just kind of going the opposite way. Which there's nothing wrong about this as long as we break our second bond. Okay, so we're making a bond. We're going to go ahead and break another bond. Let's break this bond right here. So what we'll do is draw a resonance form from that, and what we'll have is a negative right here, double bond right there, and what we'll have now is this oxygen with charge on it, and what we have to do to calculate that charge is to remember to draw out the lone pairs. So again, this original oxygen only had 2 lone pairs on it, so what we're going to do is we're going to have an oxygen with a valence of 6, so 6 minus 2, 4, 5. So this oxygen is going to be positively charged, and this carbon is going to be negatively charged. So between these two resonance forms, the one on the top is actually going to be the more stable resonance contributor, simply because thinking about electronegativity and the ability of an atom to hold electrons in its valence, what we have is this oxygen, which is way more electronegative than the carbon, and so the oxygen is going to be better suited at holding that extra lone pair, versus this carbon, less electronegative, less able or less suited to hold that lone pair. Okay, so neither one of these are incorrect, but the one that's going to be most stable is this top green version, where the oxygen has the negative charge, carbon has the positive charge. Okay, so moving on to sub-question 5, what we have is a nitro group attached to a carbanion. So in this case, we actually have 2 different possible ways of moving electrons around. So first way, we can play around with this lone pair. on the carbon, or we could play around with the lone pair on the oxygen. Again, this positive charge is never going to move in and of itself, but will only move to a different atom after we have an electron moving to something else. Okay, so let's go ahead and move this lone pair onto this carbon-nitrogen bond. Okay, that's the easiest way to move it around. If we're going to do that, then we have to break this nitrogen-oxygen bond. So we have 2, 4, 6, 8 electrons around the nitrogen. Nitrogen is also subject to the octet rule, so I have to make sure we don't have a Texas nitrogen. So let's go ahead and break this nitrogen-oxygen bond. That's one possibility. And we can draw the resonance form of that guy like this. 1, 2, nitrogen, then oxygen has the negative, oxygen has the negative, and then carbon right here has just the hydrogen, so it's now going to be neutral. And overall we have negative, positive, neutral, or they neutralize each other, and then one more negative. So overall we're going to have a negative. And so right here we have overall a 2 minus charge on this molecule, so we have to remember that nitrogen with 4 bonds to it's going to have positive charge, so that's our positive. So still we have charge balance, so that looks good. Okay, so the second possibility is that we can take this lone pair on the oxygen and push it up here, and then we could also again break this nitrogen-oxygen bond. And if we do it that way, we will get the same looking molecule. Oops. The only difference now is that this nitrogen has an oxygen right here with a negative and an oxygen with a neutral charge because we used this lone pair to form a pi bond. We still have overall a positive charge on this nitrogen, and this carbon over here on the left still has a lone pair, so it's still negatively charged. Overall, we still retained an overall negative charge for the molecule. So let's compare and contrast these two then. So for both of these, we have the nitrogen with a positive charge. So apples to apples, there's nothing different. Let's just discount it from our comparison. Okay. So the second bit that's the same is this oxygen right here that's negative versus this oxygen up here that's negative. Same thing, nothing's different. Then down here we have this oxygen that's negative versus this carbon that's negative. So that's what we were really trying to compare. Okay. So we aren't really comparing this positive or this negative because it's the same for both resonance forms. The deciding factor here is going to be this negative on the oxygen or this negative on the carbon. And again, obviously the same rationale applies here as applied up here, in that the oxygen is more electronegative and is better able to house that charge than the carbon is. Okay, so because of that, this red resonance form is going to be major, and this one down below is going to be minor. Okay, so major up above and minor down below. Apologies for my horrible handwriting on that one, but minor down below. Okay, okay, so that's those two possibilities. So let's go to question 6. So question 6, what we have is we're starting off with the charged molecule. Let's go ahead and draw the only real possible way of moving these electrons around are to take the pi and to move them onto the carbon-carbon bond that's adjacent to this pi bond. So if we did that electron movement in that fashion, what we get would be 1, 2, 3, still 4 carbons. All we're doing is moving that pi bond over to the next carbon-carbon bond. So if we have 1, 2, 3, 4 carbons, that 2-3 bond is broken, and we're making the 3-4 bond. And again, obviously, we have to account for positive charges. So if the positive charge used to be on carbon 4, the positive charge is now going to be on carbon 2. At this point, it should be relatively intuitive, but if not, you can double check just by looking at what's bound to carbon 2. So here we have a carbon with 1 positive, 1, 2, 3, 4 minus 3 is positive. We know we don't have another hydrogen attached to carbon 2 simply because up here we had 1 implicit hydrogen with a neutral carbon, so we had 1, 2, 3, 4 bonds overall neutral. So that checks out. Okay, so overall here, these are really the only 2 resonance possibilities, so these are actually kind of cool to compare. Here what we have is a primary allylic. We know it's allylic because we have this pi bond right here, and 1 carbon over on carbon 4 you have that positive. So overall this is going to be the positive allylic. Okay, allylic. If we had had a positive on a pi bond itself, on a carbon that has a pi bond, that's vinylic. But this is that special kind of positioning that we talked about. This is a name that you need to know, allylic. Okay, so this is the primary allylic. This is going to be secondary allylic. So since we're comparing apples to apples, we're comparing allylic to allylic, you don't really have to worry about the allylic part. It's there, but it's not really useful to compare. So let's just forget about that. And now it really just comes to comparing primary carbocations to secondary carbocations. So of the two, the secondary is going to be more stable. So the secondary is going to be major, and the primary is going to be the minor. Overall, pretty simple. Okay? Alright, so let's move on to the next example. Let's do question 13. So let's go ahead and draw the only other real resonance form we can draw for this guy. We're going to use this lone pair, push it onto the nitrogen-carbon bond, just like we did in the previous question 40. And we're going to have to break this carbon-oxygen bond. Same thing as before. Okay? If we do that, we're going to end up forming oxygen with negative charge. We're going to have a double bond here, nitrogen to carbon, and we're still going to have that hydrogen where it used to be because we're not showing that hydrogen bond being broken in any way, shape, or manner. Okay, so here this is actually kind of nice because the negatives and the positives align themselves with the more electronegative and the less electronegative atom. So oxygen's more electronegative than nitrogen. So it's going to be better able to hold that negative charge. So that seems to be just fine, negative on the oxygen where it needs to be, positive on the nitrogen where it needs to be. So between these two now, we're not really comparing the most stable location for the negative because we only have really one negatively charged atom on the green variant and a positive charge on the green variant. So here, if you have to choose between these two, it's always going to be, the more stable species is going to be the species that has neutral atoms versus charged atoms. So here in this case, we're going to have a neutral overall, and both of these atoms are neutral versus, in this case we have two atoms that are charged. So again, going back to this idea that we talk about over and over again, nature hates a deficit and nature hates an excess. So in this case, oxygen has an excess, nitrogen has a deficit of electrons. So in this case, they're relatively happy. They're towards that neutral middle ground. So between the two, this overall neutral molecule is going to be the major resonance contributor, and then the minor is going to be this guy right here. Okay. Yes. All right, so let's move on to the next question, question 10. I forgot about that guy. We're going to have a resonance contributor where we can, again, take the lone pair, push it onto the carbon-carbon bond, and break the carbon-oxygen bond. Basically the same thing as question 13. The only difference now is that we're doing it with carbon instead of nitrogen. So really this becomes more of an exercise to make sure you can draw resonance more than anything else. So that oxygen is going to be negative, and we're going to have a neutral carbon right here, and then we have those extra two carbons. Okay, so now we have to choose whether we would rather put the negative charge on the carbon or the negative charge on the oxygen, because there's no way to keep everything neutral. So we can't have our cake and eat it too. We have to choose one, the lesser of two evils. So in this case, the oxygen is more electronegative, better able to stabilize that negative charge because of electronegativity. That's the argument. Again, we're going across the rows, so that's a valid argument we can make. Is as we go across the row, electronegativity increases, the ability of that atom to stabilize the negative charge is going to be greater. Okay, yeah, that's pretty much it. So the major is going to be on the right, major on the right, minor on the left.